Hello everyone, my name is Horace, and in this video we're going to be going through LeetCode number 19, remove nth node from end of list. So for this problem, we're given the head of a linked list, and we have to remove the nth node from the end of the list and return the head of the new linked list with the node removed. So this seems like a very straightforward question. So let's say we have the linked list with the nodes 1 pointing to 2, which points to 3, which points to 4, and which points to 5. And along with the linked list, we're also given some n value, and this is going to be an integer from 1 to the length of the linked list. So in this case, it can be 1 to 5. So let's take the case when n is equal to 2. That means the second last node from the end of the list is going to be removed. Well, if n is equal to 2, we have to remove the second node from the end of the list. So in this case, if we go backwards from the end, we can say this is 1 and this is 2. So the node that we're going to be removing is this one right here. Okay, now that we know which node we're going to remove, we need to figure out a way to actually access or figure out when we've reached the node previous, because our strategy is going to be changing this link to simply point to the one after it. And this is exactly kind of what we want to do. And we can achieve this by using two pointers, namely a slow pointer and a fast pointer. So since we know that n is equal to 2 for this example, we want to get reference to this node here. So this is the third away from the end. And the way we can do this is by using the two pointers, as I said. So we can have a slow pointer and a fast pointer, both pointing to the head of the linked list in the beginning. And what we can do is with this fast pointer, we can move n times. So in this case, we're going to move the fast pointer once, and then we're going to move it twice. So the fast pointer now is going to be 2 elements from the start of the linked list. And the reason we do this is because we know that if we start moving both the slow pointer and fast pointers together until the fast pointer reaches the end of the linked list, the slow pointer is going to be n steps away from the end of the linked list. So this is a quick trick that we can use to get n nodes from the end of the list. And try to convince yourself that this is going to work. So we know that this distance here is going to be n. So if the fast pointer is at the end of the linked list, the slow pointer is going to be exactly at the node previous to the one we want to remove. And try to convince yourself of this fact by working on a few examples on your own. Well, now that we simply have reference to the slow and fast pointers, we can just change the next pointer for this node right here, and we can move it to the next value. So it's going to, by definition, just remove this node because we no longer have reference to it. So this is pretty much the crux of the solution. We just have to use two pointers, get the slow pointer, and then just move the next pointer of the slow pointer node to point 1 next to it. So let's consider some edge cases. So what will happen if we have a linked list with only one node? So let's say this is our only node and it's pointing to null. Well, then in this case, n has to be equal to 1. So we know that this node is going to be removed. So we can just return none or null here because the linked list will become empty after removing this node. Let's also consider the edge case where we have the n value equal to the length of the linked list. So in this case, n is going to be equal to 3. Well, if n is equal to 3, we know that it's going to be exactly the first node that we remove, since it's exactly equal to the length of the linked list. So we can just return everything after the head. So it's just head.next that we return, and we'll get the correct answer. The reason we need to account for these edge cases is because if we use this value, the fast pointer is going to be null, and we can't set the slow pointer next value to a valid node. So the time complexity for this algorithm is going to be big O of n, since we have to basically move n times for the fast pointer and then a one pass until the fast pointer reaches the end. So really, this is just a one pass solution, since the fast pointer is only ever moving the length of the linked list. The space complexity is big O of 1. We're just using pointers, the slow pointer and the fast pointer, to keep track of the nodes. So with that being said, we can go ahead and write the solution on LeetCode. Okay, we're on LeetCode and we can start writing the algorithm. So we need to take care of some edge cases. So let's take care of the one node linked list edge case. So we know that if not head.next, then we just want to return none. So this is basically when we have something like 1, which is pointing to null, and that means head.next is nothing. So we're going to end up removing the only node because n has to be equal to 1, given the conditions in the problem. Then what we can do is we can initialize the slow pointer and the fast pointer to both be pointing to the head. Then we want to shift the fast pointer n times. So what we can do is basically have a for loop. So for in range, and we want to move n times. Then we can just say fast is equal to its next pointer, and we'll get exactly n steps away from the start or the head of the linked list. Then what we need to do is account for the case where n is actually at the end of the linked list. So let's say we have 1 points to 2 points to 3, which is null, and we have n is equal to 3, because this is possible. Well, the fast pointer is actually going to be pointing to null. So this is going to cause errors for the rest of the code. So we can just take care of this case here. We can say if not fast, so fast is null, then we can just return head.next, because this is going to be removing the first or head element in the linked list. Then we can basically iterate until the fast pointer reaches the end. So fast.next, we can move the fast pointer, we can move the slow pointer, and we know that at this point, the slow pointer is going to be at one node before the one we want to remove. So we can just say slow next is equal to slow next dot next. And this is pretty much it. We can just return the head now, and we'll get the new linked list with the removed node. So we can try and submit it, and yeah, you can see the code is accepted. It runs quite fast, and this solution is big O of n, running in a space complexity of big O of 1. So hopefully this video helped you and you learned something, and I'll see you soon.